Welcome to the deep dive. Today we're looking under the hood at the infrastructure powering these huge new language models. Not the models themselves, but how they actually talk to each other across potentially hundreds of machines.
That's right. We're digging into a technical paper on something called TransferEngine. The mission really is to understand how this tool enables efficient, flexible, and maybe most importantly, portable communication between different parts of these giant systems.
Portable being the key word there.
Absolutely. Because these newer LLM setups, things like mixture of experts MOE or disaggregated inference, they need data moved in very specific, often dynamic ways. And they need to do it reliably whether you're on, say, NVIDIA hardware with ConnectX or on AWS using their EF.
And the stakes are pretty high, right? If you can't get this communication backbone right, scaling models like Kimi K2 or DeepSeek V3, these trillion parameter beasts across different clouds, well, it just doesn't work.
Exactly. The whole scaling promise falls apart.
Okay, so let's start there. The communication bottleneck. Why are the methods LLM frameworks have been using, why are they suddenly not good enough?
Well, traditionally, LLM frameworks relied heavily on what's called collective communication. Think NCCL, Torch, Dot Distributed, things like that.
Right, standard stuff for parallel training.
Exactly. And they're great for static patterns like basic data parallelism where everyone exchanges gradients in a predictable way, all reduce, broadcast, that sort of thing.
But things are getting more complex now.
That's the crux of it. These new architectures, MOE, where data needs to jump to specific expert models or disaggregated inference splitting tasks across nodes, even asynchronous RL fine-tuning, they demand really flexible point-to-point communication. One specific GPU needs to talk directly to another, maybe just sending a small amount of data, maybe at unpredictable times.
So the old collective, everyone in sync approach just doesn't map well anymore. It's a mismatch.
It's a fundamental mismatch, yeah. The collectives just weren't designed for this kind of dynamic, often sparse traffic.
Can we get specific? What are the, technical limitations? Where do collectives really fall down?
Sure. There are a few big ones. First, fixed membership. Collectives assume a stable group of participants. You can't easily add or remove resources on the fly without a big reset.
Okay, so no dynamic scaling.
Pretty much.
Yeah.
Second, they usually need synchronized initialization. Everyone has to coordinate globally just to set up the communication channel, which adds overhead, especially if the communication itself is brief or sparse.
Right.
Third, uniform buffer sizes. They often assume everyone's sending or receiving roughly the same amount of data. For something like MOE, where maybe only a few tokens go to one expert, you're still potentially allocating resources as if it were a dense transfer. It's inefficient.
Wasting resources.
Exactly. And finally, even though some libraries offer basic point-to-point things like send and receive, they often just aren't fast enough. The latency isn't low enough for these really demanding new workloads like MOE expert switching.
Okay, so the old tools are too rigid, too slow for these dynamic models. The obvious answer in high-performance computing for speed is RDMA, Remote Direct Memory Access.
Right. RDMA is the gold standard. It gives you incredible bandwidth. We're talking 400 gigabits per second, and latency down in the sub-microsecond range.
And it does that by bypassing the CPU, right? The NIC talks directly to the GPU memory.
Precisely. It cuts out the kernel overhead, which is huge for latency. The problem isn't RDMA itself. It's that different vendors implement it differently.
The hardware lock-in problem. So we want RDMA speed, but we hit this wall because the hardware isn't uniform. What are the key differences, say, between the big players like NVIDIA and AWS?
It really boils down to delivery guarantees. On one side, you have NVIDIA's ConnectX NICs. They typically use what's called reliable connection, or RC transport. The key thing about RC is it guarantees in-order delivery.
Meaning message A arrives before message B, always, if you send them in that order.
Exactly. The sequence is preserved. But then you look at AWS's Elastic Fabric Adapter, EFA. It uses a custom protocol, Scalable Reliable Datagram, or SRD. Now, SRD is reliable, the message will get there, but it explicitly doesn't guarantee the order. It provides reliable but out-of-order delivery.
Okay, so one guarantees order, the other doesn't. And that single difference is enough to break portability.
Absolutely. That's the core of the vendor lock-in. If your LLM framework is built assuming that messages will arrive in order like they do on ConnectX,
it breaks on EVA. Or at least it performs terribly.
Exactly. We see this in practice. There are specialized libraries like DeepEP for MOE that rely on ConnectX-specific features, things like GPU-initiated RDMA, which ETHA doesn't have. And then you have things like NVS-SanchMem, which works great on NVIDIA hardware, but basically falls off a cliff performance-wise on EVA because it needs that ordering.
So before TransferEngine, you essentially had to choose your hardware and stick with it if you wanted top performance for these advanced models. There was no good cross-provider way.
That's the situation they were facing. No truly portable, high-performance solution for flexible point-to-point RDMA.
All right, so TransferEngine comes along. What was their big idea? How did they manage to bridge this gap between the in-order world of ConnectX and the out-of-order world of EFA?
The core insight was finding the common ground. They realized that even though ConnectX offers ordering, you don't have to use it. Both ConnectX RC, if you ignore the ordering part, and EFA SRD fundamentally provide reliable but unordered delivery.
So they built their system on the lowest common denominator that both platforms could support reliably.
Exactly. Instead of trying to force EFA to be ordered or making ConnectX applications somehow work without order, they designed an abstraction that assumes unordered delivery from the start.
That's clever. But wait, if messages can arrive out of order, how does the receiving GPU know when a complete thought or a complete layer or whatever data chunk it needs is actually arrived? If you can't rely on sequence, what guarantees completion?
That's the really neat part of TransferEngine. Their API gives you the standard send-receive, but critically, also one-sided operations, specifically write-M. IM stands for immediate data, and the key innovation is something they call the M counter.
M counter. Okay, what does that do?
When a write-M operation successfully lands its data payload on the receiver, it also atomically increments this special 32-bit counter in the receiver's memory using that immediate data field.
Okay, so it's not about which message arrived, but how many have arrived.
Precisely. The receiver isn't checking, did message 5 arrive? It's checking, has the counter reached 4? Meaning 4 expected pieces of data have landed, regardless of their original sending order. Completion is tracked by the count of successful writes, not the sequence.
And the application gets notified somehow.
Yep, through callbacks or by checking atomic flags tied to that counter value. It allows the network to deliver packets out of order, maximizing bandwidth utilization, while the application still knows exactly when all the required data is safely there.
Very neat. And they handle other hardware stuff too, like AWS needing multiple NICs.
Right, that's another practical detail. A single ConnectX 7 card might hit 400 GBPs on its own, but on AWS P5 instances with EFA, you typically need to combine 4 separate 100 GBPs EFA and NICs attached to a single GPU to get that same peak bandwidth.
So TransferEngine handles that aggregation automatically.
Yeah, it manages the sharding across those multiple NICs, the load balancing, all of it transparently. The application just sees one 400 GBPs pipe. It's implemented in Rust, by the way, and uses pinned worker threads carefully placed across NUMA nodes to really squeeze out that low latency.
Okay, architecture makes sense. Let's talk about where the rubber meets the road. The paper shows 3 production uses. Case study 1, transferring the KB cache in disaggregated inference. Remind us why that's needed and how TransferEngine helps.
Right. Disaggregated inference is about splitting the model execution, often putting the initial prompt processing prefill on one set of GPUs and the token generation decoding on another. This saves cost. But you need to get the state, the KB cache, from the prefiller to the decoder really fast.
That cache is huge, right?
It can be massive, yeah. TransferEngine uses a primitive called submit paged writes here, designed for sending this kind of data layer by layer with very low latency.
And there was this interesting coordination bit mentioned, the UVM watcher. What's that about? How does it work with, say, CDA graphs?
The UVM watcher. It's quite elegant. It's basically a flag in memory that the host CPU monitors. The GPU kernel, after it finishes its computation for a layer like the attention projection, it writes to that memory location.
And the host sees that change.
Instantly. The host proxy thread sees the watcher value change and immediately triggers the RDMA transfer of the just computed KV cache pages for that layer. It's compatible with CDA graphs, which is essential for keeping the GPU busy.
And the receiving decoder node.
The decoder uses that expect mcount primitive we talked about. It knows how many pages to expect for that layer, waits for the mcounter to reach that number, and then proceeds with its computation. It doesn't need extra synchronization messages. It enables really elastic layer-by-layer pipeline parallelism.
Very cool. Turns it into a reactive system.
Yeah.
Okay, case study 2. Reinforcement learning weight updates. What was the bottleneck in asynchronous RL fine-tuning before?
The traditional bottleneck was, again, the collective communication pattern. You'd have multiple training workers calculating weight updates. They'd all have to send their updates to a central GPU, usually rank 0.
The gather operation.
Right. Rank 0, aggregates them, maybe averages them, and then has to broadcast the new weights back out to all the inference workers. That rank reel becomes a massive choke point. All the updates funnel through one node's network connection.
And TransferEngine changes this. How? Point to point again.
Exactly. It completely changes the communication pattern. Instead of gather broadcast, each training GPU uses one-sided RDMA writes to send its weight shards directly to the relevant inference GPUs.
So it's a mesh, not a funnel.
Yeah.
Utilizing all the network links simultaneously.
Precisely. It uses the full aggregate bandwidth of the cluster, and the performance gain is pretty staggering. The paper reports 1.3-second cross-machine parameter updates for trillion parameter models, like Kimi K2 scale models.
1.3 seconds for a trillion parameters across machines.
Yeah, they've mentioned it's over 100 times faster than typical existing RL frameworks for that kind of scale. It fundamentally changes how quickly you can iterate and adapt these huge models.
Wow. Is that purely the RDMA speed, or is there more to it?
It's both. The RDMA provides the raw speed, but they also optimize the pipeline. They overlap the data movement, like copying weights to the GPU, H2D MACPy, preparing them, quantization perhaps, with the actual RDMA transfer. So the network is always busy minimizing dead time.
Makes sense. Never let the hardware sit idle. Okay, final case. Mixture of experts, dispatch, and combine. This seems like the most latency-critical one. How did TransferEngine handle routing tokens between experts without that ConnectX-specific GPU-initiated RDMA?
They used a host proxy thread again for the coordination. Before sending the actual token data, the nodes do a quick exchange of metadata, basically, just the counts of how many tokens are heading to each expert on the other nodes.
So a small initial handshake to figure out where everything needs to go.
Exactly. This minimizes memory footprint because you only allocate buffers for the data you know you're receiving, and it tells the sender exactly where to RDMA write the token data for each expert.
But using a host proxy, doesn't that add some latency? Isn't the goal usually to keep the CPU out of the loop in HPC?
It does add a tiny bit of overhead compared to a pure GPU-initiated approach, but it was a necessary trade-off. Firstly, it's what makes the solution portable to IFA, which was a primary goal. Secondly, TransferEngine focuses on bulk transfers. Even though there's that small host coordination step, sending larger chunks of token data together allows for much better network utilization compared to approaches like DeepEP that might send things token by token.
So trading a tiny bit of initiation latency for better overall throughput and, crucially, portability.
Right, and the results bear this out. They actually achieved state-of-the-art decode latency on ConnectX-7, sometimes even beating DeepEP, and they delivered the first performant MOE implementation on EFEC. That was huge.
That's a really impressive balancing act. Okay, let's wrap up with the performance numbers. Did TransferEngine truly deliver on that promise of peak performance on both NVIDIA and AWS hardware?
The evaluations look really strong. They hit the 400 GBP's peak throughput target line rate on both ConnectX-7 and EFA setups.
So bandwidth-wise, portability achieved.
Definitely. For tasks limited by throughput, like sending those 64 kilobyte KV cache pages, both platforms saturated the network link equally well. TransferEngine didn't leave performance on the table.
And what about latency? Especially for MOE, where EFA's out-of-order nature might hurt.
EFA was definitely viable, which was the key question. In those latency-sensitive MOE decode tests, EFA's latency was only about 30% higher than ConnectX-7's.
30% isn't nothing, but it's way better than doesn't work or falls off a cliff.
Exactly. ConnectX still has some advantages, maybe lower-level hardware optimizations TransferEngine couldn't fully abstract. But that 30% difference confirms that EFA, thanks to TransferEngine's unordered design, is absolutely a practical and competitive option now for these complex, latency-sensitive models where it wasn't really before. So at the end of the day, TransferEngine really delivered. They built this reliable, unordered communication layer on top of very different RDMA hardware. It effectively breaks vendor lock-in for these critical communication patterns. It means LLM developers can now seriously consider deploying things like MOE or disaggregated inference or these rapid RL updates across different cloud environments without giving up that 400 GBP's performance they need.
So boiling it down for you, the listener, achieving things like 1.3-second weight updates for trillion parameter models isn't just a benchmark. It fundamentally changes the economics and the speed at which these massive models can be trained, fine-tuned, and deployed. It shrinks the feedback loop for model improvement dramatically. And maybe here's a final thought to chew on. We've just discussed transferring the entire knowledge of a trillion parameter model in just over a second. If models can update their understanding of the world almost instantly, how might that accelerate reinforcement learning systems? Could we see complex systems adapting to new information not in hours or minutes, but potentially approaching real time? What does that future look like?